Hello all, welcome to this course on time series modeling and forecasting using R. Okay. Now again the title that you see in front of you states causality tests and further. So again just to quickly give you a short overview of where we stand this week. So the entire focus area in all the previous lectures this week has been co-integration, right. So the main topic which we are discussing so far this week is co-integration. So firstly we started this week by explaining what do you mean by co-integration, and next when can we say that two series xt and yt are indeed co-integrated or not, right. And there we argued couple of things, that if xt and yt are individually integrated with certain order, let us say I1 or I2 etc. But if certain linear combination of xt and yt exists, let us say where beta is the coefficient, whereas beta is also called as a co-integration vector, but the other words is that if there exists a certain linear combination of xt and yt such that the linear combination happens to be I0, then one can actually say that xt and yt are co-integrated. Okay. And then we talked about couple of other things such as what do you mean by spurious regression, right. And just in the last lecture we talked about several tests by using which one can actually find out whether two series xt and yt are co-integrated or not. Okay. And there if you remember we talked about 4 or 5 different tests, let us say Engel-Granger or Johansen test, then Phillips-Oliaris, and then ARDL bounce test, etc. And all these tests, the underlying H naught is that the xt and yt are not co-integrated, while the alternative hypothesis was the xt and yt are co-integrated basically. And then towards the end of just last lecture we saw a couple of examples where testing of co-integration is sort of important to analyze both the series further. Okay. Now in today's lecture we will try to explore a few ideas about causality tests. So firstly what do you mean by causality tests, and a few other aspects related to causality tests. Okay. Alright, so firstly we have to define what exactly one means by causality tests. So the heading is causality tests. So causality tests are statistical methods or tools used to assess whether one time series can predict or cause changes in another. Okay. So this term causality is, as the name suggests, that one has to find out whether one of the variables, let us say xt, causes any change in one of the other variables, let us say yt, or even vice versa, right. So if any of the variables xt or yt causes a change in the other variable, then we can say that causality between xt and yt exists. And I am pretty sure that many of you might have heard about this very famous statement in almost all the that you hear in almost all the statistical courses of regression and so on, that regression or correlation does not imply causation, right. So even if you have high correlation between xt and yt, one can't say that xt causes yt or rather yt causes xt, right. So high correlation does not necessarily imply that there has to be some causation between xt and yt. Okay. But the focus of the entire today's lecture will be more of causation. So where one of the variable causes some change in the other or vice versa. Okay. So just to summarize one more time, that causality tests are statistical tools or techniques used to assess whether one time series can predict or cause some changes in the other. So in time series analysis, the most widely used causality test is Granger causality, right. So the most widely used causality test in time series literature is Granger causality, which determines if past values of one of the variables x contains information that helps to predict the future values of another variable, say y. Alright. So the idea about Granger causality is just to find out if there exists some causality between xt and yt such that the past values of one of the variables, let us say x, contain some information that helps to predict the future values of another variable, let us say y. Okay. Okay. So now we will sort of break it down. So we will try to understand what exactly does one mean by Granger causality in a bit more detail. Okay. So Granger causality is based on the premise that if variable x, Granger causes variable y. So we have this technical term that if there exists any causality between x and y, we will say that the variable x, Granger causes variable y, then knowing the past values of x improves the prediction of y beyond any of the information contained in the past values of y alone. So again let me break this statement down just to make it simplified. So let us say, so you have two variables x and y, okay, and assume that x, Granger causes variable y. Okay. So let us say each of the series, now let me write down xt and yt since we are dealing with time series structure. So xt and yt are two different time series, and each of these series would have its own past information, right, in form of lag. So, let us say xt minus 1, xt minus 2, etc. Similarly, yt would also have its own past lag. So, yt minus 1, yt minus 2, etc. Okay. So, if it turns out that xt Granger causes variable yt, or there is some causality between xt and yt, then knowing all the past values of x, for example, xt minus 1, xt minus 2, improves the prediction of y. So, remember one thing, the focus here is to predict y. So, which is again as usual to any regression assumption we make, right. So, xt is the independent variable and yt is a response, and the goal in regression is to predict y. Okay. So, similarly here, so assume that the goal is to predict y. So, if there exists some Granger causality or simply causality between xt and yt, then using the past values of xt improves the prediction of y beyond any of the information which might be found here in the past values of y itself. Okay. So, of course, how do you do forecasting or how do you do prediction? So, one can actually do forecasting based on its own past values, isn't it? But on the other hand, if you have another variable, let us say xt, which is Granger causing y, or there is some causality between x and y, then one can actually add to the information from the past values of x also. Okay. So, importantly, Granger causality is not the same as true causation, by the way. So, Granger causality is exactly not the same as true causation, it only assesses the predictive relationship between the variables, right. So, how could or rather how good can one predict one of the variables, let us say y, based on its own past values, of course, but also based on the past values of some other variable, let us say xt. So, under all these situations one can say that x Granger causes y, but again Granger causality is not the same as true causation between xt and yt. Okay. Alright, so now slowly we will turn our attention to the actual mathematical formulation between the Granger causality. So, again to test if x Granger causes y, we will compare two models. So, the first model is what? So, the first model is called an unrestricted model, which is nothing but a model of y which includes both the lagged values of y and x. Okay. So, the first one is unrestricted, which is nothing but a model of y which includes both the lagged values of y and x, and the second one is called as a restricted model, which is a model of y which includes only the lagged values of y. Now, again just to summarize very quickly, that again imagine that you have two time series structures xt and yt, and again as discussed in the last slide also, that xt and yt could have their own past values which are nothing but lag. So, xt minus 1, xt minus 2, similarly yt minus 1, yt minus 2, right. So, in this entire spirit one can actually talk about two particular models. First one is unrestricted, where a model of y includes both the lagged values of y as well as x, and the second one is restricted, where the model of y includes only the lagged values of y itself. Okay. Now, assuming we are testing Granger causality up to a certain lag, let us say p. Okay. So, let us say we will fix some lag up to a certain lag p, and up to that lag p we will be testing whether Granger causality exists or not. Okay. So, again assuming we are testing Granger causality up to certain lag p, then the unrestricted model happens to be this. So, yt equals some intercept alpha plus the first summation I going from 1 to p beta I into yt minus I plus the second summation j going from 1 to p gamma j into xt minus j plus epsilon t. Now, again I am pretty sure that this equation might seem difficult, but understanding each and every part is not that difficult. For example, so firstly, what kind of a model is this? So, the first model is unrestricted, and again remember what do you mean by unrestricted. So, unrestricted means that yt uses its own past values as well as past values of xt, and hence we should have both these values inside the regression, isn't it. So, one should actually have yt minus I as well as xt minus j, since the model is unrestricted, right. And once you plug both these series or the past values of xt and yt in the regression model, one should actually have those coefficients as well. So, gamma j and beta I, right. So, rather alpha, beta i's and gamma j's are nothing but the underlying coefficients of this regression structure. And similarly, if the model is restricted, then yt can't depend on past values of x. So, yt only relies on past values of itself, right. So, you have a simplified structure of the regression. So, yt equals a single intercept alpha as before, but here we should have a single summation. So, I going from 1 to p, then beta I into yt minus I plus epsilon t. Okay. So, again just to summarize, if the model is unrestricted, then there should be more than two coefficients, so alpha, beta i's and gamma j's, but if the model is restricted, then yt cannot depend on the past values of xt's, right. So, in this case we should have a much more simplified regression structure where alpha and beta i's are the only set of parameters. Okay. Alright, so how exactly does one carry forward the test, right. So, the test involves the following hypotheses. So, the null hypothesis or H naught is that x does not Granger cos y, that is all the coefficients gamma j's are 0. Okay. Now, again let me just for a second let me go back a slide and then just sort of elaborate what this null hypothesis is telling us. So, null hypothesis or H naught states that x does not Granger cos y. So, there is no Granger causality between x and y, which means that all the gamma j coefficients should be 0. And why is that? Because again if you go back a slide, then gamma j coefficients are attached to xt minus j. So, if there is no Granger causality between x and y, then this entire structure should be kind of close to 0, isn't it? So, the entire structure should be close to 0, which means that all these coefficients gamma j's should be really close to 0. Okay. Hopefully, this makes sense, because if Granger causality does not exist, there is no question of bringing this xt minus j in the model itself, right. So, in other words, all these gamma j coefficients should be very, very small or rather close to 0, such that this entire factor sort of disappears. Okay. Alright, and then similarly the alternative hypothesis is that if x Granger causes y, then there should be at least one gamma j which is not equal to 0, such that the second factor in the previous equation does not disappear basically. Okay. So, in this context one can actually use an F test for small samples or wall test for larger samples to determine if adding past values of x significantly improves the prediction of y. If the F test yields a statistically significant result, we would reject the null hypothesis, suggesting that x Granger causes y. Okay. Now, firstly couple of things to remember here as a summary. So, let us say the direction we are kind of picking here is like this. So, we are kind of finding out if x Granger causes y and not the other way around, right. So, I think this first point should be etched in the minds, that the direction is from x to y, similar to any other regression equation we have, right. And in this spirit I can actually use two tests. So, the first one is F test, which is the usual test which is nothing but ANOVA that we used in regression, and then F test could be used for smaller samples, but when the sample size is large, then one can actually apply the wall test. But either or, if one applies either the F test or the wall test, how would you kind of conclude that x Granger causes y or not? Just by looking at the value of the test statistic. So, if the value of the test statistic happens to be bigger than the underlying critical value, or if the p value happens to be lesser than the alpha, then we can say that one can actually reject the null hypothesis and simply state that x Granger causes y. Okay. And whenever the conclusion is that x Granger causes y, what is the interpretation of this statement is that past values of x also significantly improve the prediction of y. Make sense so far? Alright. So, now we will discuss some assumptions of Granger causality. So, the first assumption is stationarity. So, both the series xt and yt should be stationary. If not, they must be transformed often by differencing. Okay. So, this is a very important assumption when it comes to testing or checking for Granger causality. So, stationarity assumption again says that both the series xt and yt should be stationary to start with, and if not, they must be transformed or they must be converted to a stationary series, often by differencing. Okay. Then the second assumption is lag length selection. So, again if you remember, once we construct that regression equation, that summation ran from I going from 1 to p and again j going from 1 to p, right. So, we fix the lag length to be p there. So, again the choice of fixing that lag length, let us say p or some other number, is crucial, right, and this can be determined by using criteria like AIC and BIC. So, how exactly? So, probably I will explain in very brief kind of an idea that let us say the idea is now to fix a particular lag length, right. So, here what I can do is I can fix certain values of p. So, let us say 5, 6, 7 up to let us say 10, okay. And then by fixing all these individual values for the lag length p, I can again run my regressions every time and look at the AIC values or the BIC values. And finally, whichever AIC value is the least, I can go with that regression model or that lag length. Make sense so far? So, this is one step of choosing the lag length, because choosing the lag length is also crucial. Now, the third assumption is no co-integration. for VAR model. So, if x and y are co-integrated, then using an ECM. So, again if you remember what ECM is, so ECM is error correction model, right. Then using an ECM or vector error correction model, VECM is more appropriate. Okay. So, one of the assumptions of Granger causality is there should not be any co-integration existing between xt and yt, right. And again this is more specifically for VAR model. So, if x and y are co-integrated, then instead using an ECM or a vector ECM or VECM is more appropriate rather than checking for Granger causality. Okay. So, these are some assumptions under the idea of Granger causality. So, the first one is stationarity, then appropriate lag length selection, then there should not be any co-integration in the underlying series and so on. Now, we will talk about a few extensions of Granger causality, right. So, the first one is VECM causality or rather vector error correction model causality. Okay. So, what do you mean by that? So, just in the previous slide we saw that this was kind of a limitation, right. So, if x and y are co-integrated, then applying ECM or VECM is slightly more appropriate than checking for Granger causality. Okay. So, again we will try to emphasize a bit more on this idea that if two variables are co-integrated, one can actually use a VECM or a vector ECM, and in this case Granger causality test should include both the error correction term, which would give you the long term relationship, as well as the lag differences of the variables, which would give you the short term dynamics. So, the moment one finds out that the two series xt and yt are co-integrated indeed, then one can actually shift to using a VECM. And how should you use a VECM? That Granger causality test should include both the error correction term, that would give me the long term equilibrium relationships, and the lag differences of the variables, which would give me the short term dynamics. Okay. Then second extension could be non-linear Granger causality. So, by the way, all these are extensions of a standard Granger causality, right. So, let us say the first one is VECM causality, which assumes that xt and yt are also co-integrated. So, whenever xt and yt are also co-integrated, how do you handle Granger causality, right. Then the second one could be a slightly different modification to the standard causality, which is non-linear Granger causality. So, again of course, some relationships may be non-linear, requiring models like neural networks or certain kernel based methods to assess causality. Okay. So, if let us say xt and yt are non-linear to start with, then of course, a standard Granger causality test or rather a standard Granger causality between xt and yt might not be useful, right. So, in this case if xt and yt are non-linear, we can actually extend a standard Granger causality to something like a non-linear Granger causality, etc. Okay. Then there could be one more extension to Granger causality, which is called as instantaneous causality. Now what do you mean by instantaneous causality? So, this actually tests if changes in x at time t immediately affect y at time t, which can be explored within a simultaneous equation model framework. So, by the way, this is a very famous kind of a framework called as SEM. So, many of you might have heard about SEM structure. So, SEM stands for simultaneous equation modeling, right. But in other words, instantaneous causality means that if changes in x immediately affect the other variable, which is y, at the same time. So, changes in x at time t affect the other variable y at the same time t, right. So, all these changes or all these deviations or all these kind of intricacies should happen instantaneously, right. And such a causality can be more explored within a SEM kind of a framework. Okay. So, again I will say, just to summarize, that all these are extensions of a standard Granger causality, that what or rather how could one handle situations if let us say two series are co-integrated, or xt and yt are non-linear, right, or there exists some instantaneous kind of changes between xt and yt at a particular time t. Okay. So, now how do you test for Granger causality? So, now that we have developed a few ideas about what do you mean by Granger causality, right, and a few extension of that. So, the first test is called as the Haw-Pearce test, right. Again, this is a very famous test for checking for Granger causality. So, the name is Haw-Pearce test. So, the Haw-Pearce test is a statistical test used to assess Granger causality in the context of two stationary time series by examining their cross correlations, right. Now, again some of the important assumptions are underlined here, that both the series should be stationary to start with. So, one can actually apply this Haw-Pearce test to test whether x Granger causes y or not, with the assumption that both xt and yt are stationary time series by examining their cross correlations. Okay. And such a test, or rather the Hoppe's test, is particularly helpful for identifying if past values of one time series can improve the prediction of the other series. So, the past values of xt can improve the prediction of the other series, which is yt, often without the need for estimating a model directly. Right. So, this is just a broad summary of what do you mean by Hoppe's test and under what assumptions or under what conditions can one apply the Hoppe's test, right, and so on. Okay. All right, but then what exactly is the procedure, right? So, what exactly is the procedure of applying the Hoppe's test? So, the first step is pre-Witten each of the series. So, again we have a technical term here, it's called as pre-Witten. So, what do you mean by pre-Witten each series? Which means fit a simple autoregressive integrated moving average or rather ARIMA model to each time series separately. So, let us say if you are working with two time series xt and yt, then what one can do is one can start by fitting or modeling each of the series individually through a ARIMA kind of a model structure. Right. So, this step isolates the residuals for each series, effectively removing any autocorrelation in the data. So, even if there exists some autocorrelation between, let us say, xt and yt, which is called as cross correlations, by the way. So, once you individually model xt and yt using an ARIMA kind of a structure, then this step sort of isolates the residuals for each series, effectively removing any autocorrelation in the data. Okay. And then the second step is compute the cross correlation of the residuals. So, the cross correlation function, or in short CCF function, between the residuals of the two series is then found out or is then calculated, and this CCF represents the relationship between the unexpected or unexplained changes in one of the series and the past values of the other. So, once you pre-Witten or rather once you fit individual ARIMA models in both the series, right, then the second step is to compute the cross correlation of the underlying residuals. So, let us say you fit ARIMA model here on xt and ARIMA model on yt, then you gather both the residuals and then you compute the cross correlation of both the residuals. Now, again just to summarize, the cross correlation function or the CCF function between the residuals of the fitted ARIMA models of the two series is then calculated, and this CCF represents the relationship between the unexpected or unexplained changes in one of the series and the past values of the other. So, such cross correlations can actually tell you that whether the residuals of one of the ARIMA fits has any sort of a relationship with the other residuals of the other ARIMA model. Okay. Now, again in this Hoppe's test, what exactly is H naught? So, the null hypothesis is that there is no causality between the two series, meaning the cross correlations are 0, and the alternative hypothesis or H1 is that there is some causality between the two series indicating significant cross correlations. Right. Now, again as before or rather in all the earlier tests also that we have seen in the last lecture, the H naught stays pretty much the same, that there is no co-integration or there is no causality between the two series, right, and alternatively there exists some co-integration or there exists some causality between xt and yt, right, and so on. Okay, and now the actual procedure. So, once you frame both the hypotheses and so on and so forth, now the next thing is to formulate the appropriate test statistic. So, in this case the test statistic is nothing but a sum of squared cross correlations up to a specified lag, let us say k. Okay. So, let us say you fix some lag k and the test statistic is nothing but a sum of squared cross correlations up to that lag k. And how do you choose k? So, k is usually chosen based on the data frequency or practical relevance. So, through some data frequency approach or checking the practicality of the actual underlying data, one can actually fix the lag k. And how does one find out the test statistic q? So, the test statistic q is found out as q is nothing but t summation rho hat k square, okay, where capital T is nothing but the number of observations, rho hat xy k is the cross correlation at lag k. So, let us say you fix the lag k and the rho hat tells you the cross correlation between x and y, and capital K is the maximum lag of interest. So, once you fix this capital K, small k goes from 1 to capital K, right. So, ideally speaking, the test statistic value q is not that difficult. So, it sort of involves the cross correlations between x and y up to a certain lag capital K and the square of that. And now it so turns out that this test statistic or this statistic follows a chi-square distribution with capital K degrees of freedom. So, this q happens to have a chi-square distribution with capital K degrees of freedom. Okay. Now, what may be the assumptions of this Hoppier's test? So, the first important assumption is stationarity, right. So, the test assumes that both the time series are stationary, meaning they do not exhibit trends or seasonality. Okay. And then the second assumption is model appropriateness, that appropriate ARIMA models are fitted to each series to produce residuals free of autocorrelation. And this step is critical because cross correlations can only represent Granger causality if the series' own past values have already been accounted. Okay. So, the underlying Hoppier's test also comes with a couple of assumptions which one should kind of check for. Right. And now the second procedure is called as Xiao procedure, right, so probably the H is silent here, it is called as Xiao procedure. So, the Xiao procedure is an extended approach to Granger causality testing designed to overcome some limitations of the traditional Granger causality tests. And by the way, this was proposed by Cheng Xiao in 1981 and hence the name Xiao procedure. The procedure is especially useful for lag selection in time series data and offers an adaptable way to determine causal relationships. Now, what exactly is the procedure all about? So, the Xiao procedure combines Akaike's final prediction error, or in short FPE criterion, with the traditional Granger causality, improving both model selection and testing efficiency. So, the Xiao procedure is kind of an extension of the Granger causality by combining the traditional Granger causality by this Akaike's final prediction error in some sense. Okay. Now, again we will not go into detail due to paucity of time, and also it will be much more difficult to sort of handle all these different ideas, but I thought of just putting the Xiao procedure in front of you just to tell you that how can one extend the standard Granger causality. Okay. And now what exactly is the motivation? So, probably the Xiao procedure is advantageous because it systematically determines the best lag structure for both the variables, avoiding arbitrary lag length choices. It also uses the FPE criteria, which we saw in the last slide, which balances model fit and complexity, ensuring that the selected model is both accurate and parsimonious. Okay. So, all these kind of different ideas point to a fact that one should actually handle the entire idea of causality with a bit more detail. So, whether XT and YT are co-integrated or whether they are non-linear. So, one can't use a standard Granger causality tests, right. So, one can actually go for non-linear causality, or how do you handle co-integration, or what do you mean by instantaneous causality, right. And then we talked about Xiao procedure, etc., or we talked about Hoppier's test, right. So, all these ideas point to how do you handle causality between any of the two series. Right. Now, obviously in the next lecture this week we will kind of finish this entire idea about co-integration or causality through a practical RS session, right. Thank you.